So the midterm that will happen next week, calculators will be allowed on some of the midterm, but not all of it. So there will be like 2 parts to the midterm. You'll do the first part, and you won't be allowed a calculator on it. Then you'll hand in this first part, and I'll say, okay, now you're allowed to use a calculator on the second part. Does anyone either not have a calculator, or would anyone just generally like to have one of these TI scientific graphing calculators for the sake of the midterm? Cool. If you go up to the math department office on the 5th floor, so you get out of the elevator, if you turn right, there'll be a brown sign that says math department office. If you go in there with your student ID and give them your student ID, they'll lend your calculator. Groovy. And that applies to everyone else, not just you. Neato. I guess another thing that this means is, so some number of people have set up to take their exams through the testing center. I believe there's a piece of online paperwork you need to do in the meantime so that the testing center knows to ask me to send them a copy of the exam. So if you're doing that, I think there's a bit of paperwork you need to do that doesn't involve any paperwork. Cool. So let's get started with content. So this section of the notes is all about just little tricks you can do that tell you information about roots of polynomials. The trick we have so far is polynomial long division or synthetic division or this ad hoc division. They're all the same. And the idea of that trick is once you find a root, you can simplify a polynomial, you can factor it, and maybe you can find roots for the remaining factors. If you can, then you're done. But that required like a starting point. You needed to be able to find this initial guess for a root of a polynomial, and if you just always knew how to find that root, you just use that to solve the polynomial anyway. So you can't always find that starting root, but let's find a way to like make progress on that question. And maybe the most obvious thing that you could do if you just wanted to like guess a root would be, well, screw it, I'll try to plug in 1, I'll try to plug in 2, I'll try to plug in 3, I'll try to plug in 4. You have like a 0% chance of success. Because there are too many numbers, you can't test them all. The rational roots test is the first trick we'll develop. It will be a way of getting a finite list, a reasonably short, in fact, list of candidates to be roots of this polynomial. Cool. Let's start with that. So here's what the rational roots test says. The rational roots test says if a polynomial equation, so there's a polynomial equation. It's a bunch of coefficients next to powers of x, so each of those ad minus 1, all the way down to a0. They're just numbers. And then x to the power, you know what that means. That's x to that power. So this is a polynomial. If it has a rational solution, so what's a rational number? It's plus or minus p over q, or p and q are whole numbers. Then p has to divide a0, and q has to divide ad. And let's just put these two things into words. P has to divide a0. So the numerator of any rational root must be a factor of the constant term All right, that's what it says. The thing on the top of the polynomial, that's the fraction, that's the numerator, has to divide evenly into a0, which is the constant term of that polynomial. And q, the denominator, must divide into ad. The denominator must be a factor of the leading term, or the leading coefficient. And during the course of today's lecture, I'm not going to try to convince you that the rational roots test is true. The reason it's true isn't that fancy. It's totally understandable. If you want to go through and understand the proof of the rational roots test, there's an extra credit right at the end of this section of the notes. Go through it, and then come talk me through it. So, let's use the rational roots test to do something. Here's a polynomial equation. 2x cubed plus 11x squared minus 7x minus 6 equals 0. Let's use the rational roots test to see all possible rational numbers that might be solutions to this polynomial equation. So I guess that means we need all the possible choices of p, all the possible choices of q, and then we'll stick a plus or minus sign in front of p over q. Cool, let's do it. So, I'm going to use a shorthand right here. I'll use the shorthand in a second. The numerator p, it must divide into, let's see, it has to divide into the constant term of the polynomial. So what's the constant term of that polynomial? -6, which in terms of divisibility, that's the same thing as just asking about 6. So maybe I'll say that just to make it easier to write. Do we know all the possible things that divide evenly into 6? Yeah, what are they? 1, 2, 3, and 6. So P, equals is fine, is one of 1, 2, 3, or 6. Same thing for Q. Q divides into, so Q has to divide evenly into the constant term. What's the, no, not the constant term, the leading coefficient. What's the leading coefficient of this polynomial? 2. So Q has to divide into 2. So what are all the possibilities for Q? 1 and 2. Oh, neat. So, all of the rational numbers are the form P over Q, so they're one of these divided by one of those. So let's just list all of those possibilities. We'll notice some redundancy, so we'll be able to erase some things. We'll get a list of possibilities that won't be too long, and then we'll just test them. So, possible rational roots were the things of the form plus or minus P over Q. So any of these 4 things divided by any of those 4 things. That'll give me 8 options. With the plus or minus, it'll become 16 options. Which is like verging on a lot. Like I wouldn't want to do any one thing 16 times. But really there will be some redundancy, and it's not just one person in the room, so we'll break up some work in a second. So all the values for P divided by all the values for Q. So I guess that's 1 over 1, also known as just 1. 2 over 1. 2, 3 over 1, 6 over 1, 1 over 2, 2 over 2, 3 over 2, and 6 over 2. And it is important to include all the plus or minus signs, because any one of these could be positive or negative. And I said there would be some redundancy in this list. What is the redundancy you see in this list? 1 and 3 are listed twice. I don't need to list them twice. So those I can eliminate. Hey, that reduces the number I need to test by some. 1, 2, 3, 4, 5, 6. With a plus or minus sign, that's 12 possibilities. So here's what the rational roots test says. The rational roots test says you don't need to bother checking something like 13 to see if it's a root of this polynomial. It knows for a fact it can't be. You don't need to check like 6 over 7. It's not allowed to be a root of this polynomial. Those are the only possible rational numbers that might be roots. It doesn't tell you anything about like square root of 2 minus 7. That's not rational. But let's check those to see if those are roots. And if this next page is correct, So 2x cubed plus 11x squared minus 7x minus 6 equals 0 has a complete list of possible rational roots of that list. So if I want to check for roots of a polynomial, there's a finite list that's a reasonable place to start. And I've broken it up with those dividing lines because I think that the right thing to do is, well, break up the walk sum. Maybe I'll do 1 and minus 1. Well, no, 1 minus 1. Yeah, cool. Plugging in 1 is like the easiest thing to do, right? Other than maybe plugging in 0. It'll be 2 plus 11 is 13, minus 7 minus 6. Does that total out to 0? All right. Have we just found ourselves a root? Yeah, cool. And we only expect there to be 3 roots. It's a degree 3 polynomial, so we're a third of the way done already. Plug in negative 1. So that'll be negative 2, because negative 1 cubed is negative 1, plus 11 because of the squared, plus 7, because I'll plug in negative 1, minus 6. That look like it's equal to 0? No, I think it'll be positive, whatever it is. So this is pretty clearly now something that you would not want to do all the computations on your own. So here's how I'm going to break up the walk. I see many of you are starting in already, so this will be maybe mildly annoying. Plus or minus 2? Plus or minus 3? Plus or minus 6? Plus or minus 1/2? And any of you that are calculator carriers, now's a great time to use it. I wouldn't want to do all this by hand. I'm well aware that you probably could raise these numbers to the 6th power and add them up. So once you test your numbers, go ahead and shout out and tell me it is a root or it is not a root. Say that more. 3 and negative 3 do not walk. You probably got the actual number, but I kind of don't care what the number is. It's not 0. Cool. Well, 2/3 of the way done. And at this point, you should be feeling like really hopeful because it's a degree 3 polynomial. Each of those rational numbers would result in there being like a thing you could divide into this. So you divide one of them in, you get a degree 2 polynomial out. You divide the next one in, oh, the only thing left is a degree 1 part. You could definitely find that root. So I know it has that thought rational root, so another one of these should walk. Plus or minus 2? Excellent. Did not result in a 0. Did not result in a 0. 6 is the last one left on the list. Negative 6 walks, as in the result is equal to 0. Positive 6 does not walk. Neato. So is there even any reason for me to check plus or minus 3 has at this point? What's the degree of this polynomial? 3. So what's the number of roots that it could have? 3. So those couldn't be roots anyway. So I don't really need to check them. And so I think I won't. Instead, here's what I'm going to highlight. This is obviously something that you should use a computer for. And in fact, you should probably do everything you can to automate as much of this as possible. And if this were like a coding heavy or computer science class, maybe one of the things we'd discuss is like, I don't know, writing a for loop to just do this all at once. It's not that, so here's what I'll do instead. That has been implemented already, and it's built into Wolfram Alpha. That QR code will take you to this link, which has this evaluate command. If you evaluate this degree 3 polynomial, where x is a thing in that list of 12 items, it'll just spit out all the answers at once. It looks like 0, well that came from -1. 0, that's the 1, 2, 3, 4, 5, 6, 7, 8 thing. 1, 5, 6, 7, 8 thing. -6, was that one of the ones you said? Excellent. And then, does this disagree with one of our computations?
-2 positive 1/2.
Yeah. Awesome. So here's the really embarrassing thing. Since it's on paper, I can't edit that QR code anymore. It will always take you to this. Now do I see that extra 0? Mm-hmm. Excellent. So, right, technology is useful, but it's only actually as good as you are at using it. Nice. So, we have now found all of the roots of this polynomial. We've just completely solved this equation. We got 2x cubed plus 11x squared minus 7x minus 6 equals 0 has solutions. X equals 1, -6, and -1/2. And in fact, I'd say we even get a little bit better than that. Oh, you couldn't see what I wrote, but you know what I just wrote. You get a little bit better than that. This also tells you how this polynomial factors. Roots of a polynomial correspond to linear factors. So because 1 is a root, x minus 1 is a factor. Because -6 is a root, x plus 6 is a factor. -1/2 is a root, so x plus 1/2 is a factor. Those are all the linear factors. So this is like really close to just being equal to the polynomial. The only shortcoming is if you want to expand all this out, your lead coefficient would be 1. What is the lead coefficient of this? 2. So what should I multiply it by? 8. So the rational roots test, when it walks well, can walk really well. But what do you think? Will it always walk? No. Sometimes it won't tell you what you want it to tell you. And it still tells you something when it fails. But let's see an example when it fails. So let's apply the rational roots test to 3x cubed plus 2x plus 2 equals 0. So let's go through the exact same game. What are the possible values for p? Say louder. 1 and 2. What are the possible values for q? 1 and 3. Oh, so that's not even as many. So all the possible rational roots are plus or minus 1, plus or minus 2, plus or minus 1/3. Commas are important here. Plus or minus 2/3. All right, so we have our list of candidates. And let's play the same game. Let's evaluate the polynomial at these 8 inputs. See if we ever get a 0. And you know what? I'm not going to do this by hand. I think I'm going to go over to the computer, go to this Wolfram Alpha link, and see if I can successfully type in this stuff. I'm reasonably confident that if I can't, then you'll tell me what I do wrong. All right, so I want to evaluate this polynomial. 3x cubed plus 2x plus 2. I want to evaluate at 1 and -1. I'll leave those alone. 2 and -2. 1/3 and -1/3. 2 over 3 and negative 2 over 3. And right, it also does this nice putty point thing where it now shows you what I've typed in a more readable notation. Is that polynomial that I actually wanted to evaluate? Okay, good. Is that the list of candidate roots that I wrote down? There's the result of the evaluation. Is there a 0 on that list? Oh, so are any of them actual solutions? Nope. So at this point, have we completely solved this degree 3 polynomial equation? Nope. We do know one thing though. So here's like the exciting thing that we can conclude. This polynomial has no rational roots. So there's no need to even bother plugging in any rational number that says no rational number will result in this polynomial being equal to 0. What's some other stuff we could do if we wanted to like investigate the roots of this polynomial? What's one thing you can always do if you're allowed any tool you want? Yeah, we could graph the thing. That's what you were saying, right? Yeah. Okay. I'm okay at reading lips, but not good. So, I could use Wolfram Alphabet. Desmos is the one I've been using more regularly. Let's graph this thing. 3x cubed. Nope, that's one. Plus 2x plus 2. So, by looking at this graph, how many solutions does this thing seem to have? One. And at this scale, maybe it looks like it's around negative 1.5-ish. At that scale, maybe it's closer to negative 0.6282. Do you think it's exactly equal to 0.6282? Nah, it can't be. 0.6282 is a rational number. This doesn't have any rational roots. So it's some irrational number that's close to that. So via computer graph, the solution is about 0.6282. And maybe I'll include the word real there, because this is a degree 3 polynomial. So it's going to have not just one real root. It will, in one root, it'll have 3 roots. The other 2 roots are complex. Cool. Nice. So there's the second trick we have. We have the rational roots test, and just like any of these tricks, it works really well sometimes, and it doesn't tell us much most of the time. The next one is one that we can use to control where the solutions to a polynomial will live. So like, what region of the real number line we should expect to see solutions. This is Descartes' law of signs. And here's the statement. So Descartes' law of signs says the following. Let P of x be a polynomial. And I always write my polynomials so that the powers of x are in descending order, but you don't need to. You can accidentally put the highest order term last if you want. It's important for this theorem that you don't do that. So make sure all the terms are written in descending order. The number of positive solutions to P of x equals 0 is equal to either the number of times the coefficient changes sign as you go left to right, or that quantity minus something even. So let's just see what that means. So here is a degree 3 polynomial. In fact, it's the one on the previous page. According to Descartes' law of signs, let's compute how many positive solutions this might have. So that means we need to compute how many times the coefficients change sign. From 3 to 2, did the coefficient change sign? Not just change. Did it change from positive to negative or negative to positive? No. No sign change there. Both positive. Plus became plus. From there to there, is there a sign change? Nope. So how many times did it change sign? 0. So there are no sign changes. So that means the number of positive solutions is equal to either 0 or 0 minus an even number. So it could be 0, or there could be negative 2 roots, or negative 4 roots, but would that mean anything? Does it make sense to say this equation has negative 4 solutions? No, so it just has no solutions. So P of x equals 0 has no positive solutions. And happily, we just graphed this thing. Does that agree with the graph? Yeah. And here's another thing that this tells us. This graph only goes up to x equals 10. Maybe, just maybe, around x equals 10 million, it turns around and comes back. Descartes' law of signs is saying, no, it doesn't. It's not going to come back to the x-axis at all, or positive at all. So there's what Descartes' law of signs tells us, and we can get more information out of that. For example, we might want to know how many negative solutions a polynomial equation has. And here's how you can figure that out. That'll be the same as the number of positive solutions to P of negative x equals 0. Does that make sense? Yeah, right, because if x is positive there, then negative x is negative. And negative x is apparently a solution. So, if you want to get the number of negative solutions to P of x equals 0, think about the number of positive solutions to P of negative x. To do that, let's just write out what P of negative x is. So that'll be 3 times negative x cubed plus 2 times negative x plus 2. Have I successfully plugged in negative x for all the x's in that polynomial? All right. Are there any simplifications that can be made now that that's happened? Yeah, what happens when you cube a negative? Just the negative pulls out. So that'll be negative 3x cubed minus 2x plus 2. How many times does the coefficient change? Just the once. It goes negative to negative, that's not a sign change. Negative to positive, there's a sign change. 1 sign change. So, there is 1 negative root. Cool. And you can do more than just that with this. So let's see what we know right now, just based on this, not looking at the graph or anything. If there's x equals 0, we know that to the right of x equals 0, there are no solutions. We know that to the left of x equals 0, this polynomial has 1 solution. Descartes' law of signs lets us zoom in a little bit and see more information. And on the one hand, we've looked at a graph. We know that the solution is like 0.6 something, right? I don't have any memory to remember more than 1 digit. In fact, I'm not sure about that 0.6, but it doesn't really matter. Descartes' law of signs will can let us determine a little bit more. If you want the number of solutions to P of x equals 0 that's greater than a constant c, well, that's the same as the number of positive solutions to P of x plus c equals 0. Do you agree? right? If x is positive in there, then x plus c is bigger than c? Yeah. So, let's see that in practice. I don't want to do -1. I think I want to do +1. No, I want to do -1. So, let's expand out p of x minus 1. That'll tell us how many solutions this polynomial has which are bigger than -1. So, we can do that. P of x minus 1, well, that'll be 3 times x minus 1 cubed, Gesundheit, plus 2 times x minus 1 plus 2. Have I successfully plugged in x minus 1s for all the x's? Yeah, and I guess there's some, like, foiling out to do. Gesundheit. So, I think I'm going to start by doing this off to the side. Maybe you're the type of person who has, like, the binomial expansions all memorized out. Maybe you are, maybe you aren't. If you're not, then you can still just compute it on the spot. X minus 1 times x minus 1 times x minus 1. Well, I know how to FOIL this part out. That'll be x squared minus 2x plus 1. And then I want to multiply that by x minus 1. So far, so good. And let's just do that. X squared times x is x cubed minus 2x squared plus x. Now multiply everything by minus 1. Minus x squared plus 2x minus 1. And I've just written things in those two columns so that it's easier to now do the next subtraction. That is x cubed, Gesundheit, minus 3x squared plus 3x minus 1. All right. So that means this is 3 times that. 3x cubed minus 9x squared plus 9x minus 3 plus 2x minus 2 plus 2. All right. Is that good enough for us to apply Descartes' law of signs to? Are the powers all written in decreasing order? Not really. All right, so let's combine some like terms, and like there aren't that many terms to combine, but we need to combine them. This simplifies down to there's only one cubic term, 3x cubed. Is there any other squared term than 9x squared? Cool. Minus 9x squared. Are there any x terms other than 9x? 2x. So that's plus 11x then? Are there any constant terms other than minus 3? Yeah, but I guess they cancel. Now are the coefficients, now are the powers all listed in decreasing order? All right, how many sign changes are there? Let's see, 3 to 9, there's a sign change. It goes from positive to negative. Negative 9 to 11. Did it change sign again? Yeah, it went negative to positive. So you count both ways. Positive to negatives get counted and negatives to positives. 11 to negative 3. Did it change signs again? So how many sign changes? 3. 3 sign changes. So there are 3 or 3 minus an even integer. So what's another number that's 3 minus something even? 1. So this is a case where Descartes' law of signs gives us ambiguous information. There could be 3 solutions to this, or just 1. Solutions greater than negative 1. And it's greater than negative 1 because I subtracted negative 1. So let's add that to the picture. to the left of -1, there are 3 or 1 solutions. Would it make sense for there to be 3 solutions bigger than -1? No, because then those 3 solutions, well, either they'd be in between -1 and 0, which would be bad because there's only 1 solution to the left of 0. There are no solutions bigger than 0. So this gives us really good information. These computations tell us there's exactly 1 solution here. Cool. So, now that we've gone through all that, you can get lots of good information about Descartes' law of science by performing a repeated walk like this. Let me tell you what sort of things I'll expect on like exams and stuff. I'll expect you to be able to tell me how many positive solutions a thing will have and how many negative solutions a thing will have using Descartes' law of science. That seem fair enough? Nice. And I want to emphasize one additional thing because this is an error I see made consistently on exams and stuff. The number of positive solutions to p of x equals 0 is equal to either the number of times the sign of the coefficients change or that same number minus an even integer. And that's really important, right? We found 3 sign changes there, but there's not enough space for there to be 3 solutions to the right of x equals -1. So 1 is the only option it could have been. So that minus an even integer matters a lot. Feel good? Nice. So we have these tools. They independently give us some information. Let's see if we can play with these tools in order to actually solve some polynomial equations. Do you think that you can always just use these tools to solve every polynomial equation? I mean, not really. Like the Descartes' law of science thing, that will let you zoom in once you get an idea of where the solution is, and like, really get a good idea of where it is. But it's never going to tell you exactly where the thing is in finitely many computations. And this thing I mentioned that Galois did means that you have no hope of ever doing that, no matter what strategies you use in only finitely many steps. Some polynomials don't have algebraic solutions. Well, they do have algebraic solutions. They don't have solutions you can find algebraically. So, let's put these together and try to solve some polynomial equations. So with my remaining 10 minutes, I think I'll go through this page. The open-ended homework assigned today looks a lot like this page. So let's go through this, and then you'll be very well prepared for the homework assigned for this section. So let's find the solutions to this polynomial equation. X to the 5th minus 7x to the 4th plus 19x cubed minus 37x squared plus 60x minus 46 equals 0. And let's just go through it by answering the following questions. So first question, what's the degree of this polynomial? 5. So it's the greatest number of real solutions it could have. 5. And in fact, I know it has exactly 5 solutions as long as I'm willing to count with multiplicity. And I'm also willing to count complex solutions. All right. So that means if I can find 5 roots, then I'm done. And let's get some positive / negative information. Using Descartes' law of science, how many positive roots could there be? Yeah, say it louder. Or? So the rule is 5 is good. 5 is good. It could also be 5 minus an even integer. So 5 or 3 or 1. So what does that tell us? That tells us that maybe there's only one positive solution. If I find a second positive solution, I know there has to be a third. If I can find 4 positive solutions, I know there has to be. How about negative solutions? Well, maybe before I move on, Like I didn't actually do any walk there. People want me to actually say what happened there? Cool. So, Descartes' law of signs says count the number of times the coefficient changes from positive to negative. So let's do that. From x to the 5th to negative 7x to the 4th, is there a sign change? Yeah. It goes from positive to negative. I need to count that. That's a sign change. From negative 7 to positive 19, did the sign change? I need to count that. So there's 1, there's 2. From 19 to negative 37, do I need to count that? Yeah. Negative 37 to positive 60, do I need to count that? From 60 to negative 36, do I need to count that? Cool. Now I guess how many tally marks did I make? 1, 2, 3, 4, 5. And that's like handy because like that's an easy count to make. Like there's no arithmetic you need to do there. To figure out how many negative roots there are, you'd have to do a little bit of work, but not much. To determine the number of negative zeros, so in blue, this is the number of positive roots. Let's also determine the number of negative roots. So to determine how many negative zeros there might be, we have to write out p of negative x, and then figure out how many times the coefficient of that changes sign. And we could maybe do that in advance without writing anything. In fact, definitely you could, but I'm going to write it out, and then we'll just count how many times the thing changes sign. What happens when I stick a negative inside of an x to the 5th? It just pulls out. It's an odd number of negative signs. So this is negative x to the 5th minus 7x to the 4th. What happens when I stick a negative sign inside of an x to the 4th? That particular negative sign doesn't matter. So there's still this negative sign out front. So minus 7x to the 4th plus 19x cubed. But it's a cube, so the negative will pull out of the cube. Minus 19x cubed. This one's squared, so it will just stay negative. Minus 37x squared minus 60x minus 36. Did that feel too fast for anyone? That seems sensible? All right, let's count how many times the sign changes. How many times does the sign change on those coefficients? No times. It's always negative? All right, so how many negative roots might there be? None. So this is like the best case scenario for Descartes' law of signs. That's the best information it can tell us. There are no negative roots. So if someone, for example, the rational roots test says, here, negative 3 might be a root to this polynomial, you can say, no, I know for a fact that it's not. So with that in mind, let's move on to the rational roots test. Let's get a list of candidates to be rational roots, and then we'll see what progress we can make. All right. So, and maybe I'll list it this way. I think I've got enough space for 3 lines. Oh, so this is the shorthand that I was alluding to earlier that I think I said I would write, but then never did. Sometimes I'll say, instead of writing down p divides evenly into something, I'll just write p, a vertical line, for divides evenly into, and then that's something. So p has to divide evenly into, do I want the leading coefficient or the constant term here? The constant term. And I get that's the opposite of what's intuitive. Right? You would want p to divide into the leading coefficient. At least that's what I would want, but that's just not the right thing to put there. P divides evenly into the constant term. So p divides evenly into 36. What are the factors of 36? Well, maybe I'll start 1. 36 is even, so 2. And maybe it's even good to like start at the other end too. 1 times 36 is 36. 2 times 18 is 36, so 18 is a factor. And in fact, maybe you see more factors there. Give me more factors of 36. 3 and 12. All right. What more? 4 and 9. 6 and 6, but I don't need to list a factor twice. All right, so there's a complete list of all of the possibilities for P. That's annoying, it's kind of long. What are all the possibilities for Q? Well, maybe we'll start with this. Q divides evenly into the leading coefficient, which is 1. All right, whenever you just don't see anything next to the x, that means there's a 1 there. 1 times x is x. So, all the possible rational roots, all possibilities, are x equals plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 9, plus or minus 12, plus or minus 18, plus or minus 46. So that looks like a lot of things, right? It's 2, 4, 6, 8, 10, 12, 14, 16, 18 possibilities. Could I do anything like really easy to reduce that number of possibilities now? Sorry, like you both said something and I could see that you said something. It was very good. Yeah. On the previous line, I said there are no negative roots. So there are no negative roots. And the rational roots test didn't know that. We had to ask Descartes' law of signs to tell us that. But we can combine those two bits of information. So now there are only 9 things that we have to plug in. Oh, right. That clock is fast. I have 2 minutes. So on the one hand, we could manually plug each of those in by hand, maybe using a handheld calculator. How many people think on the homework where I have you do this type of stuff, you're going to use this evaluate command in Wolfram Alpha? Yeah, I mean, you don't have to. You can do it by repeated computation or using some other technique if you want. But I think for now, I will do that. Let's go back here. Let's evaluate. X raised to the 5th minus 7x to the 4th plus 19x cubed minus 37x squared. I don't like the packing up already. I still have a minute. Plus 60x minus 36, where x is equal to, and I only need to list the positive, 1, 2, 3, 4, 6, 9. All right, there are any zeros on the list? There are 2 of them. X equals 1 and x equals 3 are roots. Seem like a start? So let's just ask ourselves this before I let you go. Do you think we're done? We only found 2 roots, I expect 5. So here's what we will do at the start of next time. This tells us that there's a factor we can divide it. We'll divide that factor. This tells us there's another factor we can divide it. We'll divide that factor. That'll bring us from degree 5 down to degree 3, which will be better. Then we'll check for repeated roots and do some more synthetic until we get to degree 2. Then we'll use the quadratic formula, and we will be done. So, in fact, if you followed that enough to do it, I'll encourage you to do it. Figure out all the roots to this polynomial. And then we'll talk to it next time. Oh, and if anyone did not wind up with one of the review sets for midterm 1, I got some right here. Oh, I have have some more.
Yep.
Excellent, thank you. Oh, cool. Appreciate it. Excellent. I think you want to put out one of these. Oh, excellent. Even better.